Okay, today we're going to talk about logarithms and other bases. When we say other bases, we're talking about other bases other than 10. And of course, with 10, you have your common log, and we don't even show the base sometimes when we write a logarithm that's a common log. But we're also going to review inverse functions. Remember when you switch the x and y and solve for y? We're going to take a look at that, and let's get started. So, for example, one thing that we need to remember is x to the negative 2, negative exponents. You don't want to leave your final answer with a negative exponent. What is that? And as we had on the test, that's 1 over x squared. Okay, what about 3x to the negative 2? We talked about this one before also. Well, in this case, it's only the base of the negative exponent that gets moved to the other side of the division line. So the x negative 2 becomes x squared in the denominator. Notice that the sign changes to positive, but the 3 is not impacted by a negative exponent, therefore it stays on top. Okay, so 5 to the negative 3 is 1 over 5 cubed, and of course 5 cubed is 125. So we would convert that, and that would be our final answer for that. Okay. Now, let's go over that log chart. This is a most helpful chart. And one of the things that it says, it has, first of all, log xy equals log x plus log y. That is your basic logarithm principle. That's why they created logs, so that you could add, because, for example, x to the m times x to the n. Yes, what is that? Well, that would be x to the m plus n. And remember, logarithms follow the principles of exponents. Logs are exponents. So that's why we have log xy equals log x plus log y. And log x over y equals log x minus log y. Well, what about this next thing on the chart? 5 to the x equals 5 to the y. And that's true only if x equals y. Well, why is that? Because you can't raise 5 to a different power and have it equal to 5 to yet a different power. So these have to be the same. Okay? Well, the same thing is true with logs. If you have log base b, and that's x, then it's going to equal log base b y. If that's true, because this says equal, these two things are equal. If these are both logs to the same base, then again, x has to equal y. You follow? Okay, there's another thing called natural log. That's usually written with small or case letters ln. And all that is, we talked about the natural base of e, so log base e equals the natural log, and that's how you write it, just ln. So ln means log base e. And remember, e is just a number, 2.718. It's a constant, and of course it's an irrational number, so it continues on without repeating or terminating decimals, but nonetheless it's just a constant number. Okay, the next thing on your chart is converting. And of course this is super important. Exponential to log form. Okay? And an example of that would be log 5 x equals y. All right? And how do we convert that to exponential form? We know that logs are exponents. We know that the base is 5, so this is 5 to the y, and that equals the argument. Do you remember? This is the base, this is the argument, and this is the exponent out here. So when we convert, that's how it's done. This is the exponential form with the exponent, and this is the log form. These are the same thing in two different forms. Okay. Finally, not quite finally, the change of base formula. We're going to talk about that today. So if I have log 7, 5, argument is 5, that is equal to log 5 over log 7. Okay, this used to be more important than it is today because our old calculators couldn't handle log 7, 5. Your calculator, the Inspire, will actually ask you to put in the base. But we didn't used to have that, and of course this was very important at that time. It's still important because when you're manipulating expressions, you may want to make this conversion maybe this way, or going back to this, or going that way. Either way, but we need to recognize that those are the same thing. By the way, this can be any base, but these bases have to be the same. In other words, if this is log base C, then this has to be log base C, okay, for this to be true. And you can check that out in your calculator with log base 7, 5 equals log base whatever 5 over log base that same whatever 7. All right? Remember how the exponent works if you have log b a raised to the x power, all right, then that is equal to x log b a. In other words, all you've done is bring that exponent out to the front. And this you will find is very helpful when you're converting back and forth here, depending on what your numbers are. When you're trying to simplify expressions, you can go either way on this, moving the number from the front to the exponent, or vice versa, moving the exponent to become the number in the front. Okay, well that pretty well covers that part. Now there were two other little things that I've skipped on that chart that we're going to talk about today. And that is log base b, b to the x equals x, and b log base b to the x equals x. Now, these are important to allow you to simplify, because if these two numbers are the same, then this all dissolves and just becomes x. Again, if this number is the same as this number, then it becomes x. Let's do examples. Log base 6 of 6 squared equals 2. Why? Because these two numbers are the same. That allows us to do that. Well, what if I had log 6 36 squared? Could I simplify that? Yes, I could. because I want these two numbers to be the same. They're not now, but 36 is 6 squared, isn't it? So that would be log base 6, 6 squared, and then you still have that squared. So that's 6 to the 4th, log 6, 6 to the 4th, and that equals 4. Okay, what about this one over here? What if I had 5 log base 5, 3? What does that equal? Well, what does it say? If these two numbers are the same, that equals 3. Oh, that's nice. Very good. All right, let's go back and review some inverse functions. What if I had f of x equals 3x minus 8? What's the inverse? Well, this is y, but I'm going to switch x and y. This f of x is y, so it now becomes this. Remember this? Now I solve for y, so that's x plus 8 over 3 equals y. And remember, we write that with a -1 up there, showing that that's the inverse. And of course, that could be written like this. All right, let's do another one. What about f of x equals 1/2 x plus 5? Okay, well, I'm going to switch the x and y. This becomes x equals 1/2 y plus 5. X minus 5 equals 1/2 y. What do I do to get rid of that half? I'm going to double both sides. 2x minus 10 equals f. There's the inverse. All right, let's try this one. What if I had f of x equals 7 to the x? Uh-oh. Well, remember the inverse of exponentials is logs. So what I'm going to do here is convert this to log form. Okay, this is y equals 7 to the x right now. And when I convert that to log form, remember logs equal exponents, so that's going to equal x. All right, and the base of the exponent was 7, so this is 7, and this is y. Do you see how I did that? I simply converted this exponential statement to a log statement, recognizing that logs are exponents. So the exponent in the exponential is the x, so log equals x. The base of the exponent was 7, that's the base of the log. And then the argument is this y over here. But that's just the conversion. Now to get the inverse, I switch the x and y. So what does that become? Y equals log base 7 x. And of course, we already knew that to a certain extent because 7 to the x in exponential form is log base 7x in inverse. Logs and exponentials are inverses, and remember, they're going to graph as reflections across that imaginary line, y equals x. Okay, let's do another question. Let's just simplify something like, what if I had 15 log base 15, 3. Well, what is that? Because these are the same, this is just equal to 3. Boy, those simplifications are wonderful. What about this? Natural log of e to the x. Well, natural log means log base e to the x. These two numbers are the same, so again, this is just x. Okay, good luck.